Good morning. Good morning. People online, hello. Good morning. Can you hear me?
Yes, we can.
What is the last subtopic we have done? We spoke about the we spoke about the variation of the activity also, right? How the number of undecayed nuclei in a sample varies, and also how the activity of a sample varies with time. We have spoken about. Correct? Are there any questions from homework? No. Right. Finally, I think we would have done this question. Correct? Right. Right on the next subtopic. Half-life. Half-life. Right? It is the time taken. It is the time taken. It is the time taken for the number of undecayed nuclei in the sample to become half. It is the time taken for the number of undecayed nuclei in the sample to become half. Right? You have heard this for your O-levels. Half-life of radioactive sample means the time taken for the number of undecayed nuclei in the sample to become half. So for an example, if there are n number of undecayed nuclei in a sample, and let's say the half-life is 2 years, that means the number of undecayed nuclei in the sample will become n over 2 after 2 years. It becomes half. After another 2 years, it will become again half, and it will become n over 4. Correct? And after another 2 years, it will become again half of that, and it becomes n over 8. Do you remember this? So basically, half-life of a radioactive sample means the time taken for the number of undecayed nuclei in the sample to become half. Okay? So we are going to come up with an equation for that here. That is what we will learn here. Now, guys, we know n equals n naught e to the power minus lambda t. Right? Where n is the number of undecayed nuclei in the sample after time t. N naught is the number of undecayed nuclei in the sample at the beginning when the t is equal to 0. And lambda is the decay constant. What is decay constant? The definition of decay constant? Check. Probability of a nuclei decaying in 1 second, in a unit time. That is decay constant, and t is the time. So now if I take n equals n naught e to the power minus lambda t, that means when the t is equal to t half, when the time is equal to t half, what we take as t half is the half-life. When the time is equal to half-life, the n will become half n naught. When the time is half-life, okay, the number of undecayed nuclei in the sample will become half of the initial value. So if I use that here, if I use n equals half n naught, n naught equals n naught into e to the power minus lambda t. So then I will cancel the n naughts on either sides, which is e to the power minus lambda t is equal to half. Half equals e to the power minus lambda t. You can recall your grade 9 maths. If e to the power minus lambda t is equal to half, e to the power lambda t is supposed to be 2, the reciprocal. So, which means lambda t is equal to L into, am I right? So, lambda t is equal to L into means I'll take this t as t half, half life. I'll label it t half. So, lambda t half is the notation for the half life. Okay, is lambda 2. Sorry, lambda t half is equal to L into. So, the t half is equal to L into over lambda. Correct? And becomes half in naught. Half in naught equals in naught into e to the power minus lambda t half. So half equals e to the power minus lambda t half. So e to the power lambda t half will become the reciprocal, which is 2. So lambda t half is L into t half is equal to L into over lambda. Exactly. So this is how you find the half life of a sample. This is a relationship between the half life and the decay constant. Take it up. Okay. Right. There's half-life is now. I said it is a time taken for the number of undecayed nuclei in the sample to become half-life. It can also be defined as it is the time taken for the activity of the sample to become half. Okay. Make a note. Half-life half-life of a radioactive sample is also defined as the time taken for the activity of the sample to become half. Okay. Right. Please write down a question. Calculate the decay constant for the following isotopes. Calculate the decay constants for the following isotopes. That are commonly used in school laboratories. Part A. Radium-226. Half-life is 1602 years. Okay, there's now here's it. Now wait. Tell me this. What is the unit of activity? Becquerels. What is the unit of half-life? Half-life can be seconds, it can be minutes, it can be years. No, it can be anything that is the unit of time. Half-life is time, right? Then what is the unit of decay constant? The unit of decay constant. Decay constant lambda. It can, now what is the, by definition, the decay? Yeah. Decay constant is the probability of nuclei decaying per unit time. So it can be per second or per minute or per day or per week or per year. It can be anything. Okay. So if you want it to fit in with the SI units, it has to be per second in an equation. So now let's say for an example here, in this case, we are told to find the decay constant where we know T half is equal to ln2 over lambda. So lambda is going to be equal to ln2 over T half. Correct? So one thing is, I can just straight away take it as ln2 over T half is 1602 years. I'll just use 1602. Then my unit is going to be year to the power minus 1 per year. Okay. If you want it to be in per second, we have to convert this 1602 years into seconds. So we can assume an year to be 365.25 days. Okay. Multiply by 365.25 or 365. Convert it into days. And each day is 24 hours multiplied by 24. And each hour is 3,600 seconds. Again, multiply by 3,600. If you do that conversion, you will be getting the answer in per second. Correct. So I will take the first one is just in per year. So that is going to be ln2 over 1602, which is 4.327 or 4.33 into 10 to the power minus 4 per year. Part B, strontium 90, half-life is 28.8 years. strontium 90, half-life is 28.8 years. Okay, so I will take this one in per second, so that is going to be then T half is, sorry, the lambda is L into over T half, that is L into over the T half is 28.8 years, which is 28.8 multiplied by, I'll take it as 365, just 365 days, or 365.25 multiplied by 24 hours multiplied by 3600 seconds. That will be 7.63 into 10 to the power minus 10 per second. Okay. So, what should I take otherwise? Every year has 365 days. Okay. So on average, an year has how many days? Yeah. Okay, tell me this, guys, how many of you understand that it has to be 365.25? What? Others don't get it? Huh? Ayyo. Where's your maths? 3 years of 365 days, and the fourth is 366 days. Okay, so this is a cycle. Every 4 years, this is what's happening. So if you take a period of 4 years and find the average, that is going to be 365 plus 365 plus 365 plus 366 divided by 4. That will be 365.25. So number of days on average per year is 365.25.
So I understand what you're saying, but we've never
Huh?
used that. I understand what you're saying, but like we've never used
Okay.
that. That's
Yeah.
the thing.
So if you have never
No,
used, we should never.
so if we use 365, is it wrong?
No, okay, calm down. I just told
Okay, so then
365.
zero, stop confusing. It's okay.
It's not confusing. You are just learning the right thing. How is learning the
Yeah.
right thing? Okay. Right, guys, part C.
So that means we can also write 366, right?
Now 366, how can you take 366? That is, does it make sense? Once in 4 years, now you get 366.
So the probability that is the fourth year, so
Do the part C. Cobalt 60, which has a half-life of 5.3 years. So just do it and get it. Baby work. Okay. Right. Fine, guys. There's page 30, question 21.
So I got 1.58 times 10 to the power minus 5 hours.
Per hours.
Yeah, in power.
So can you do the before question?
Which one?
I think he wants to you to do C, sir.
Well, 60 we can take it as lambda equals it'll into over the half-life is I will just take it as 5.3. So the unit will be per year. That will be 0.131. That is the decay constant. Right, page 30, question 21. Potassium 40 is a radioactive isotope. Potassium 40 can be, can be decayed by beta emission. Beta minus emission means beta emission. Complete the nuclear equation for the decay of potassium by beta minus emission. So guys, it becomes calcium. Now see, if you take a nuclear equation, the nuclear number has to be conserved and the proton number has to be conserved. So which means beta minus is, we know it is minus 1, 0. Okay. So if it is 40 here, it has to be 40 here. And it has to be 20 minus 1 is 19. It has to be 19 here. Correct. So it's 40, 19 K, 40, 20 calcium, and beta particle is minus 1, 0. With a charge of minus 1 and a nuclear number 0. Fine. Occasionally, okay, just keep that part B. Go to part C. Part C. A fertilizer contains potassium chloride. The activity of a sample of the fertilizer due to radioactive potassium was 48.6 becquerels. Activity is 48.6 becquerels. It is claimed that the time taken for the activity of the sample to fall below the background count rate would be more than 9.9 for 9 years. Claim that the time taken for the activity of the sample to fall below the background count rate would be more than 9 into 10 for 9 years. I will do this. Deduce whether this claim is correct. The background count rate is given 0.42 becquerels. Half-life of potassium is given 1.25 into 10 for 9 years. Now look at this. I will do this. Look at the screen. I want to see what is the time taken for the activity to come down to the background count rate. How long does it take? So for that, I will use A equals A naught e to the power minus lambda t. Listen to me. Guys, A, we are looking at the time taken for the activity to come down to 0.42 becquerels. So final count rate is, activity is 0.42. Initial activity is 48.6. E to the power minus, I don't know the lambda. Okay. Lambda into t. And also for this equation, listen, don't write. I told you not to write. I also gave you another form of this equation using the log. ln A equals ln A naught minus lambda t. Correct. I can use this as well. So now that means ln final activity is 0.42 equals ln the initial activity is 48.6 minus lambda into t. The t is what I want to find. But I don't know the lambda as well. But to find the lambda, we know that the half-life is given. Since I know the half-life, I can find the T half is equal to L into over lambda. Lambda is going to be equal to L into over T half. That is L into over T half is half-life is 1.25 into 10 to the power 9 years. So that is going to be 5.545. 5.545 into 10 to the power minus 10 per year. This is a unit of lambda. Okay, I deliberately didn't convert it into per second, I just left it in per year. The reason is they have told that the time taken for the activity to fall below the background count rate would be more than 9 into 10 to the power 9 years. They have given the time that they are talking is in years. So I want to find the time taken for the activity to go down to that value in years. I want to find this t in years. Okay. Since I want to find that t in years, I want the lambda to be in per year. Understand? If I had converted this lambda to per second and substituted here for the lambda, then the t I'm going to find will be, you will be getting again in seconds. But you need to compare it with something which is given in years. Understand? Right. So I found the lambda. I'll use that lambda here, which is 5.545 into 10 to the power minus 10 into t. So I'm going to find the t from this, which will be 5.545 into 10 to the power minus 10 t will be equal to ln 48.6 minus ln 0.42. ln 48.6 minus ln 0.42. Which is 8.56 or 8.57 into 10 to the power 9 years. This is the time taken for the activity of the sample to come down to the background count rate. But they are telling, it is claimed that the time taken would for the activity of the sample to fall below the background count rate would be more than 9 into 10 to the power 9 years. No, I'm not going to agree with that. My statement is no. It is less than 9 into 10 to the power 9 years. Okay. Take it out. So write the conclusion. The claim is incorrect. That's enough. The claim is incorrect. Okay. Any questions, anyone? Page number 36. The question is, cesium-137 is a major source of radiation from radioactive waste.
So
A
which
nuclear
question number?
page number 36,
Okay.
which is question number 24, part C. Cesium-137 is a major source of radiation from radioactive waste. A nuclear fission reactor produces about 24 kilograms of cesium-137 each year. A website states that 24 kilograms of cesium-137 has the same activity as 2000 kilograms of radium-226. Assess whether this statement is correct. Half-life of cesium is given. Mass of cesium atom is given. Activity of 2000 kilograms of radium-226 is given. 1 year is given in seconds, which is 3.15 × 10⁻⁷ seconds. Give it a try. U is 1.67 into 10⁻⁻27 kilogram. The atomic mass. Guys, wait. Before that, do this one. Page 46. That is also yeah, that you can do. Give it a try. Page 46. Okay, this can be done in two ways. One is, now say the activity of a sample of actinium 225 is 7.4 into 10 to the power 7 becquerels. When it is prepared, calculate the number of actinium atoms in the sample 7 days later. Half-life of actinium is given 9.9 days. One thing that I can do is, I will find the initial number of undecayed nuclei in the sample using A equals lambda in. Okay, A equals lambda in. So, but we don't know the lambda. I can find the lambda here. Lambda equals L into over T half. So lambda is going to be L into over the half-life is given 9.9 days. I will leave it in days because this question is in days. L into over 9.9 will be 0.0700. So basically 0.7 per day. That is the lambda. So, sorry, 0.07. So I know the initial activity, which is 7.4 into 10 to the power 7. That divided by the lambda, which is 0.07. That will give you the initial undecayed number of nuclei, which is which is 1.057. Okay. Into 10 to the power 9. This is the number of undecayed nuclei in the sample too at the beginning. So we want the number of actinium atoms in the sample after 7 days. Now you can use N equals N naught e to the power minus lambda d. N naught is 1.057 into 10 to the power 9 into e to the power minus lambda is I have taken 0.07 per day. The reason is this, the t that they have given is 7 days. Okay, remember that, keep that in mind well. If this t is in days, this lambda has to be in per day. The t is in seconds, lambda has to be in per second. Okay, those two have to match. Six point 48 into 10 to the power 8. Correct? That is one way of doing it. What time is the class? What time is the class starting? From where are you coming? Ah. Okay, fine. So what was your question? Sometimes yes, they will give you the conversion rate. Yeah, mostly no, yes. Okay, that is one way. Another method is we could have found the activity. We know the initial activity. Find the activity after 7 days. Okay, and then use A equals lambda n to find the n after 7 days. Okay. Done. You want me to do? Close enough. Let's see. That's because of we round off. So if I take a equals a naught e to the power minus lambda t, after 7 days, it will be 7.4 10 to the power 7 into e to the power minus lambda is 0.07 into t is 7. That is 7.4 into 10 to the power 7 into e to the power minus 0.07 into 7, which is 4.533. Hold on. Into 10 to the power 7. Yes, tell me. Because the 7 is in days now. So this lambda has to be per day. Okay, this is the A. And then with this A, use A equals lambda n and find the n. Okay. Per second. Hold on. I use A equals lambda n. A was in becquerels. Lambda was per day. Guys, can you please listen to me? Those who got the answer, hold on. This, when we initially use A equals lambda n, this activity was in becquerels. Becquerels means what is the unit? Per second. Becquerel is per second. But we have the lambda here, we have taken here per day. So if you want to find the initial n using this equation, this lambda has to be per second. Okay. And then you find you have to, now this is 0.07 per day. No? So per second means you need to divide this by 24 and divide it by 3600 if you want to get it in per second.
So shouldn't it be multiplied?
Per day, right? Yeah, per day, right? Divided by 24 into 3600 per second.
So shouldn't it be multiplied?
No, that is if you are converting day to seconds. That if you are converting days to second, you have to multiply. But here we are converting per day to per second, means you need to divide. Okay, anyway, my point is, since you have to do two conversions here, I feel like this method will give you the answer easily. Here you don't have to do that. Straight away you can find. Look at this one. A equals A naught e to the power minus lambda t. Your initial activity is 7.4 into 10 to the power 7 e to the power minus lambda we will take 0.07 per day into t is 7. So this will give you the activity after 7 days, which is minus 0.07 into 7, which is 4.533 into 10 to the power 7. Now this is in becquerels. Okay, this is in becquerels. Now to find the number of undecayed nuclei, A equals, we use lambda in, where the lambda is L into over T half. So now A is 4.533 into 10 to the power 7. Lambda is L into over T half, where the T half is 9.9 days, multiplied by 24 hours, multiplied by 3600. This will be the lambda in terms of becquerels or per second into N. So the N will be 5.59 into 10 to the power 30. So got this answer. That is here the lambda, I had it in per day. Sorry? Yeah, that is, we are getting here in this equation. The A is I'm finding, A naught we have taken in becquerels, e to the power minus lambda T. This lambda is per day, T is also days. Those two will cancel out. Okay, yeah. That is sorted. Then you are getting the A here in becquerels. But here you don't need to do the unit conversion. Even if you do it, that's right. But if you are doing the unit conversion, you have to convert both lambda and T. Lambda has to be per second, T has to be seconds. Get it? Then after getting that A, I'll use A equals lambda n. But the problem is now, A is here in becquerel, so I want the lambda to be in per second. Okay, please take it down.
Sir,
Yeah,
say they give us the activity and the initial activity, right? And we want to use
Yeah.
this equation A is equal to A naught, this one minus E minus lambda T. And so when we get the answer for lambda, do we get it as seconds or days?
that depends on the T. If you have used T as days, then the lambda will be per day. If you use T as seconds, lambda will be per second. These two will be the same unit.
Okay.
Let's go through it. If you have a question, ask me. Okay. Yeah, what is the question? Yeah. Yeah. If you multiply that by, hold on. There, the mistake we made is we didn't convert this lambda to per second. No. Yeah, but too much confusion in that. No? Just this has definitely more clarity. Okay. Done. Guys, page 50. Can you give a try? Page 50. That's question 32, part B. A sample of potassium chloride initially contains 1.1 into 10 to the power 22 atoms of potassium 40. Half-life of potassium 40 is 1.25 into 10 to the power 9 years. 1 year is 3.15 into 10 to the power 7 seconds. Show that the activity of this sample is about this much. So guys, lambda equals L into over T half. Now, they want the activity in becquerels means. That means it is per second, right? So if you want it in per second, T half has to be in seconds. It is L into divided by T half is half-life of potassium is 1.25 into 10 to the power 9. A sample of potassium chloride initially contains 1.1 into 10 to the power 22 atoms of potassium 40.
So should we do part 2?
Yeah, do both parts. Okay. L into over T half is 1.25 into 10 to the power 9 years. To convert it into seconds, you multiply by 3.15 into 10 to the power 7 seconds. So that will give you the activity of a atom, but they want to show. So the lambda will be L into over 1.25 into 3.15 into 10 to the power 16, that is 1.7604 into 10 to the power minus 17 per second. That is the lambda. So the activity will be A equals lambda in. That is 1.7604 into 10 to the power minus 17 multiplied by 1.1 into 10 to the power 22. That is 1.94 into 10 to the power 5 becquerels. Okay. And then the next part says, it is claimed that after a period of 50 years, the activity of the sample would be less
So I
than the
got
activity.
1.89 times 10 to the power 9 becquerels.
Let's see. Less than the activity of a typical school source. Assess the validity of this claim. Your answer should include a calculation. Activity of the school source is 1.85 into 10 to the power 5. So we'll check the activity after 50 years using A equals A naught e to the power minus lambda t. Now, look at this. Guys, we have, if I want to find the activity after 5 years and compare it with and see whether it's less than 1.85 into 10 to the power 5 or not. So initial activity is 1.94 into 10 to the power 5 becquerels into e to the power minus, listen to this. If I'm going to use lambda, which we have found in the previous part, that is in per second, then the t has to be in seconds. You have to convert 50 years into seconds. Or if you are going to use the t in seconds, then you need to find the lambda in per year. Understand?
So you
But
mix
since
it up, sir. You said if you find t seconds, you have to lambda it should be years. If t is equal to
No,
years, we have to put lambda equals years.
t is in years, lambda should be in per year.
Yeah, you
If
said
t,
second and year.
since we have the lambda in per second, which is 1.76 into 10 to the power minus 17 per second, I will convert the 50 years into seconds, which is 15 to. They have already given the conversion rate 3.15 into 10 to the power 7.
So
3.
what I did is I converted lambda into years, but I did it in the calculator. I didn't write it down. Is that wrong or what?
You need to show the
The working.
substitution. Yeah. Which will be
1.89 times 10 to the power 9.
it's the same, no? 1.94 into after 50 years.
So how, sir?
Yeah, it is almost the same. Why? Then look at the half-life of potassium given. 1.25 billion years. 1.25 into 10 to the power 9 years. So the activity to become half, it takes a billion years. And you're talking about a 50 year. So comparing to a billion year in 50 year, the drop in the activity will be almost negligible. Am I right? So that is the reason if you do the calculation here, you're getting almost the same thing. That means over a period of 50 years, the activity is not going to change, or that change is so insignificant. Correct? So the question was, it is claimed that after a period of 50 years, the activity of the sample would be less than the activity of a typical school shows. The activity of the school shows is given. My conclusion is no. No.
So could you do it if you with years, sir?
With years,
Yeah.
if you do it with years, it has to be this way. A equals A naught is 1.94 into 10 to the power 5 into e to the power minus lambda t. So lambda is ln2 over t half, which is ln2 over t half is 1.25 into 10 to the power 9. This is the lambda in per year multiplied by the t is 50. Okay. It should give you the same answer. E to the power minus ln2 over 1.25 into 10 to the power 9 multiplied by 50 into 1.94 into 10 to the power 5. Same thing. 1.9399, same thing. Okay.
So last
Yes.
time I wrote the exact same thing, I got a much different answer.
I think something wrong with your calculator, not with you. Okay.
Thank you, sir.
Yeah, not with you. Any questions, anyone? Any questions? Right, then page 54. Page 54, part B. Now this should be a piece of cake.
So even for this, the Becker, these are in becquerels, right? There is activity. So we don't have to convert the lambda or the t to seconds.
Hold on. Give me a minute. Those who did it, are you getting 5.99 years? Okay, hold on. 5.99 years is 5.99464357 is the exact value. Hold on, people. Here the unit conversion will not be needed. Look at this figure. A equals A naught e to the power minus lambda t. So we are told to find the time taken for the activity to come down from 4.07 into 10 to the power 4 t to 1.85 to 10 to the power 14. What is the time taken? Simple. Correct? They have told blah blah blah, replacing the source when the first sterilizing when the activity comes down to this value. So simply what you need to do is the time taken for the activity to fall from this value to this value. Okay, listen. So this is the original equation, A equals A naught e to the power minus lambda t. This is another version of that same equation. Ln A equals ln A naught minus lambda t. Okay. So in this original equation, this A and A naught both are in becquerels. Those two will cancel off. A and A naught are in becquerels. Now what our lookout is to make sure this lambda and t are in the same unit. If t is in seconds, lambda has to be per second. If t is in years, lambda has to be per year. Correct? So now ln A is 1.85 10 to the power 14, ln A naught is 4.07 10 to the power 14, minus lambda is ln 2 over t half. So since I want the final answer, the t to be in years, I want the lambda to be in per year. Since I want the lambda to be in per year, this ln 2 over t half, the t half I have just substituted in years, 5.27. Understood? So that gives me the lambda in per year. This is my lambda, ln 2 over 5.27 is the lambda in per year. That into t is what we have to find. Find the t here, 5.99 years. Any questions, people online? Hello? Really? I'm getting 5.9946. Maybe I have rounded up. Oh no. No. I have got the exact value with the exact figures given. It's 5.9946. That means you have done some conversions and you have done some round off. I have taken the absolute values and I'm getting 5.99464357. So to three significant figures, it has to be 5.99 years. Okay. Right. Then guys, then
So should we do 6? I mean C. Should we do part C?
Yeah, do part
Okay.
C. Okay, when in use, the cobalt 60 source is shielded with lead. The graph shows how the transmission of gamma radiation depends upon the thickness of the lead shield, thickness X of the lead shielding. So the count rate from a source must be reduced from 4 into 10 to the power 14 to 1.2 into 10 to the power 14 becquerels. Reduced with the lead shielding of thickness 1 centimeter would be sufficient to achieve this. That's an easy one. Guys, 1.2 into 10 to the power 14 over 4 into 10 to the power 14 as a percentage is how much? 30%, right? 30%. So they're asking to reduce the activity of the source by 230%. 230% is a thickness of 1 centimeter of lead enough. Reduce with the lead shielding of thickness 1 centimeter would be sufficient to achieve this. So with 1 centimeter thickness, if you see, the activity will come down to what percentage? What is the percentage there? 10, 20, 30, a little more than 30. Yeah, so what I found is the count rate from a source must be reduced to this value, no? The new value as a percentage of the original value. No. I have taken the new value as a percentage of the original value. So this is the percentage of the activity compared to the original activity. So is 1 centimeter enough? Not really. With 1 centimeter, you can reduce the activity to a value between 30 and 40%. Am I right? So which means if you want to reduce it up to 30%, you will be needing something more than 1 centimeter. Actually, it's 1.1 centimeter. Can you see it? 30% is here. 30% is here. To reduce it to 30%, you need a thickness of 1.1 centimeter. And write the statement. Thickness of 1 centimeter will be insufficient. Thickness of 1 centimeter will be insufficient. A thickness of 1.1
So how did you
centimeter.
get that is 30 and that's 40, sir? There are like
Thickness of
11
1
boxes between 100 and 10.
10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so 30% is here. This is 30%. At that 30%, you need a thickness of 1.1 centimeter. Right? Fine. Because then page 59. Page 59. Can you? Question 38. Cesium-137 is a radioactive isotope found in used fuel rods from a nuclear fission reactor. It is a beta emitter with a half-life of 30.2 years. Complete the decay equation. So guys, beta minus particle has a notation of -10. So it will be 137 here and 56 here. When it is removed from a fission reactor, a fuel rod contains this much of nuclei of cesium-137. Sorry? Calculate the activity of the fuel rod due to the decay of the cesium-137 20 years after removal from the reactor. 1A is given this much of seconds. Right. Okay. When it is removed, it has this much of nuclei. So A equals lambda in. So the initial activity will be lambda is ln2 over t half. ln2 over t half, which is, how much is half-life? 30.2 years. But I want it in seconds, which is 3.15 into 10 to the power 7. I want the lambda here to be in per second because I want the activity to be in becquerels into the initial n is 1.36 into 10 to the power 24. Now this is the initial activity in becquerels, which is 9.909 into 10 to the power 14 becquerels. Now this is the initial activity. Okay. So we are told to find the activity of the fuel rod after 20 years. So I'm going to use A equals A naught e to the power minus lambda t. A naught is 9.909 into 10 to the power 14 into e to the power minus lambda. Now the lambda is ln2 over t half. ln2 over t half, now I will take it as half-life 30.2 years. The reason the t is, now I'm going to take it in years, which is 20 years. Okay. That is going to be 6.26 into 10 to the power 14 becquerels. Have you got this answer? Yes. Can I know who has got this answer? What about the others? Where are you struggling?
Yes, I got it, sir. But see, in my calculator, it's giving the answer in 10 to the power 23, right? But then it's that small 10, it's not the big 10.
Small thing?
Yes, I'll show.
Not the big.
I'll send you a picture. I'll send you a picture in
No. But whether it is a
WhatsApp.
small 10 or a big 10, 10 to the power 23 is wrong.
No. I'm saying for this one, what they call this? Okay, what I did was I found the number this n in 20 years, right? And then I used is equal to lambda n. So then I got 6.26 times 10 to the power 14.
Okay, you got this answer now?
Yeah.
Did you
No,
get this
what I'm
final
saying
answer?
is when I'm using the equation that n is equal to n naught minus minus lambda t, it's giving the answer in small 10, not big 10 for some reason.
Now I'm also getting in small 10 only. Is it small?
Yes, but then see, okay, if you minus that answer, right, by like 6.26 times 10 to the power 14, it doesn't equal 0.
I mean, do you all understand what he's saying?
No, see, okay, see. What I'm saying is,
No,
if you minus
I only can
6.26 times, see, if you minus 6.26 times small 10 to the power 14 minus 6.26 multiplied by big 10 to the power 14, you don't get 0.
Now, in the cal, where do you find this small 10?
I don't know where you're going to find it. So it's C, but they give the answer in small 10, right?
No, I don't have that key. Okay, that is fine, no? Ah, okay. Okay. Here, you have this button no, in your calculator. Take a black mark and cut it off. Just color it off. Don't use it. Okay, done.
No, Sam, what I'm saying is that small 10 to the power 14 is not equal to big 10 to the power 14.
It is zero here, see. Okay,
Okay, okay.
did you see it?
Yeah,
Can
yeah,
you
yeah.
see? Fine, part C. When cesium 137 decays, it emits gamma radiation. Explain why the emission of gamma radiation is more serious hazard than emission of beta radiation. The gamma radiation is more penetrating. It can cause cancer. It's cancerous. It can. Yeah, penetrating ability is high. Use your common sense and write something to get the 2 marks. Right, you can take a break. See you in 15 minutes. There's page 65. Page 65, part C.
Page 45.
65. Cool, no?
So which question is this, sir?
Page 65. Are you getting this answer? 74,054 becquerels. Yes. Calculate the activity of the sample 1 day later. Part B, for part 2, are you getting 70,550 becquerels? Yes. People online, hello. Any questions?
Yes, sir. No.
No, no. Okay. Is page 36. Page 36.
So page 36, right?
Page 36, part C.
So here, why are they giving us the masses?
Think about it. Give a try. I'll give you a couple of minutes. Okay. 10 minutes. Okay. I think those who don't do chemistry, do you know what is 1 mole? Do you know what is Avogadro
Yes, sir.
number?
Yeah.
Okay. The others do it with you. Yeah. Right. Cesium-137 is a major source of radiation from radioactive waste. A nuclear fission reactor produces about 24 kilograms of cesium-137 each year. The website states that 24 kilograms of cesium-137 has the same activity as 2000 kilograms of radium-226. Check the statement is correct. Half-life of the cesium is 30.2 years. Mass of a cesium atom is given 136.9 U. Okay. activity of 2000 kilograms of radium-226 is given 7.33 into 1 10 to the power 16 becquerels. So the activity of 2000 kilograms of radium is given. So we need to compare with this value the activity of 24 kilograms of cesium-137. Activity of 24 kilograms cesium-137. So the activity is equal to lambda into n. Okay. So to find the lambda, the half-life is given 30.2 years. So the lambda is equal to ln2 over t half, which is ln2 over half-life is 30.2 years. That's 30.2 into 3.15 into 10 to the power 7, which will be 7.286 into 10 to the power minus 10 per second. That is the lambda. Okay. Now lambda is done. I need to find the n. To find the n, okay. Now they have given mass of a cesium atom is 136.9 nu. One atom is 136.9 u means 1 u is 1.66 or 1.67 to the power minus 27 kilogram. This is the mass of one atom. Then what is the mass here? 24 kilograms. So it is going to be number of nuclei is going to be 24 kilograms divided by the mass of an atom, which is 136.9 into 1.66 into 10 to the power minus 27. That will tell you the number of nuclei in the sample.
So what is 1.66 times 10 to the power minus 27?
That is 1 u, 1 atomic mass unit in kilograms. 1.66 in 10 to the power minus 27. Anyway,
So did they give it to us or what?
yeah, that's given. That's given in the data sheet. So that gives you 1.056 into 10 to the power 26 atoms. So the activity will be A equals lambda n. Lambda is 7.286 into 10 to the power minus 10 per second. N is 1.056 into 10 to the power 26. So this will be the activity in becquerels. This is 7.69 into 10 to the power 16 becquerels.
So could you do it the chemistry method?
No need.
Please,
There
sir.
are a good number of students who are here not doing chemistry. So
Yeah, but then
let's
there are a
not.
number of students who are doing chemistry also.
But no need. No? You do that in the chemistry class. Right? Have you got this answer?
Okay. So, but what you want us to do is find the moles and multiply that by the Avogadro constant, right?
Right. Fine. I hope now you can deal anything with this activity and
So the statement will be just say
or there's a we have to do a comparison, no? They're asking they have given activity of 2000 kilogram of radium 226 is 7.33 into 10 to the power 16. We are getting 7.69 into 10 to the power 16. We can say yes, it's almost same or something. Or you can also say no, it is more
But
than
it is
the,
a big major difference, right, sir? Because multiply
Yeah.
with 10 to the power 16.
I have a strong feeling markings can be accept both final statements. Either you can say yes, they are almost the same, or you can also say no, the activity of CCM is a bit more than the activity of radium. That is also fine. They are not worried about the statement. They just want to know how whether you know to get this value. Okay. Right, fine. So guys, that's enough from this. Write down the next subtopic. Binding energy. Guys, I told you we are having a test from Unit 4 this month. Huh? Yeah. What? January? So we will be having it next Sunday. Okay, Saturday we will be having the class. Sunday we will have a test on Unit 4. Okay, so be prepared. I'll let you know. I will update the exact time in the group. So be prepared for next Sunday. Okay. Right. So write on the next topic, binding energy. Sorry? No, can't. Binding energy. Right? It is the energy required for a nucleus. For a nucleus. To separate all its nucleons. To separate all its nucleons. To infinity. To infinity. It is the energy required for a nucleus to separate all its nucleons to infinity. So guys, if you take a nucleus, it has protons and neutrons. No. So now let's say there are about 136 nucleons, protons and neutrons together in a nucleus. So now there is binding between those. Okay. So now if you want to separate those nucleons, if you want to separate them, you need to supply energy. Okay. You need to supply energy to separate them. So the amount of energy that you need to supply to separate all the nucleons to infinity. What is meant by infinity is where there's no force between them, where they are isolated. To separate to that extent, the amount of energy that you need to supply is what you call the binding energy of the nucleus. Okay. It is the energy required for a nucleus to separate all its nucleons to infinity. Fine. Write down the next subtopic. Binding energy per nucleon. So that is common sense. Binding energy per nucleon means binding energy divided by the nucleon number of nucleons in a nucleus. Binding energy divided by the nucleon number, that will tell you the binding energy per nucleon, right? It is the binding energy divided by the nucleon number. It is the binding energy divided by the nucleon number. Full stop. Right below that. It is a measure. It is a measure. It is a measure of the stability of a nucleus. It is a measure of the stability of a nucleus. Full stop. If a nucleus has a higher value for binding energy per nucleon, if a nucleus has a higher value for binding energy per nucleon, higher value for binding energy per nucleon, it means it is more stable. It is more stable. And vice versa. So if the binding energy per nucleon is a high value for a particular nucleus, that means that nucleus is very stable. If it, on the other side, if the binding energy per nucleon is a low value for a nucleus, means it is less stable. So guys, this is a famous graph of binding energy versus nucleon number, right? This is the y-axis is binding energy per nucleon. This is the mass number or the nucleon number. So it has a graph shape like this. Has a shape like this, where you will see I am at this peak point. And at this peak point. So iron is one of the most stable nucleus out of everything where the binding energy per nucleon is high. On the other side, these ones have a least binding energy per nucleon, and also when it goes towards the right thing, the binding energy per nucleon will be reducing. Okay. So now when a nucleus is unstable, okay, when a nucleus is unstable, it will undergo either nuclear fission or fusion to become more stable. You know what is fission and fusion, right? Fission is a larger nucleus splitting into two lighter nuclei, and fusion is two lighter nuclei fusing together, combining together to form a larger nucleus. So that will happen in such a way naturally to increase the binding energy per nucleon. Okay, so if you see these ones, okay, their nucleon number is high. Their nucleon number is high, these ones. So what they want to do is, they want to reduce their nucleon number and get somewhere here. They want to reduce the nucleon number. So if they want to reduce the nucleon number, they have to undergo nuclear fission or fusion. Fission. So the nuclei somewhere in this end, they will undergo nuclear fission. They split into two lighter nuclei. So their nucleon number will reduce. So the nucleon number is reducing means the binding energy per nucleon will increase. Correct? Similarly, the nuclei on this side, they want to increase the nucleon number. So to increase the nucleon number, they need to undergo what? Fusion. Understood? Right. First, draw this graph. It doesn't have to look exactly the same. The shape is what just needed. Label the axis. This is mass number or the nucleon number in the x-axis. That is binding energy per nucleon. The quantities are not necessarily, you don't need to put these values in the y-axis. No need to put the values in the y-axis, no need the values. Just understand that iron will be at the peak. Iron has a nucleon number of 56, if I'm not mistaken. When nuclear number decreases, binding energy, which part are you talking about? If it is to the left of iron, when the when the nuclear number is decreasing, binding energy for nuclear is decreasing. Decrease. Right to left. From here to here it's increasing. From here to here again it's decreasing. Slowing down. If you ask me why one is its nature based on the position of the nucleon and the forces. These peak points of course there's a different story which you don't speak about. It's a characteristic of the material. But here we learn about something else. It should be right.
So nuclear fusion and fission.
Fission is a larger nucleus splitting into two lighter nuclei. Fusion is other way around. Two lighter nuclei from, I'll give a note right. Iron has the highest binding energy per nucleon. Iron has the highest binding energy per nucleon, and it is the most stable nucleus.
So fission and fusion, is it like the same elements fuse, or is it like two different?
Different. It is
And
the
it's
most
when
stable.
the nucleuses fuse, right? Nuclear fission. What exactly is it?
Tell it again, I didn't hear you.
What exactly is nuclear fission or fusion?
We'll speak on the next day. The next subtopic is that. Now complete
Okay,
this part.
we're learning.
The nuclei to the left of the iron. The nuclei to the left of iron. The nuclei to the left of iron will undergo nuclear fusion. the nuclide to the left of iron will undergo nuclear fusion to form a larger nucleus. And be more stable. Full stop. Nuclide to the right of iron. Will undergo nuclear fission and be more stable. Fission will create smaller ones. Anyway, next week we'll speak about it. Right, okay, guys. It won't decay. Right, okay. So guys, I will update the exact time for the class, the exam on next Sunday. But next Saturday we have the class as usual. Next Saturday the regular class is there. Bye, see you, take care.
So homework?
No homework, go through the questions again. Redo the questions what we need today. Bye, see you.